Hi.
We're from the learning lab. We're wondering if we can just talk to your students for a little bit before you start rolling. Just to tell them that we have tutoring available.
I love that, yeah, yeah, that's a great idea.
Okay.
What's your name?
Nick,
Nick, okay.
and this is Trish. Trish used to teach you for genetics.
Very cool, okay, well, yeah, sure, how about, I mean, I guess we can wait until 4:30 if you want to
Yeah,
make sure.
yeah, that's fine.
I guess we'll see.
Yeah,
Okay.
at the same time, I know you need the class time, so.
Do,
whenever
yeah.
you want to start.
I think it's equally important that, everybody knows about the Learning Lab, so.
Okay,
So we can, cut a few minutes off of our time, so,
okay.
for you guys, for sure. Yeah. Well, yeah, look like you're on a mission standing out there. I was like, I wonder who these people are. Yeah.
Yeah.
It's good. It's good. Welcome, everybody. We have a few guests with us today from the Learning Lab just across the way in Building 2000. So I'm going to give it away to Nick and Trish. They're going to tell y'all what you should be doing every time you're not in this class, maybe once or twice every week. Go ahead, Nick.
Sweet. Yes, so we're here just to share with you, in case you're unaware, that ACC has a free tutoring lab. We have these at every campus. So the one on our campus is in building 2000 over here. If you take the elevators, they open up where we are, which is just some big clear glass doors. We have like a communal space, big open space with circular tables. And it's pretty informal. It's a little bit noisier than the library. There's some talking and tutoring going on. But it's a great space to know about, even if you're not necessarily sure you need tutoring. You can go there, you can use, you can print. We have computers if you need to grab anything from online before or after class, or before or after lab. But we also do a lot of tutoring there, and that's our main thing. Excuse me. This is a free service for y'all. It's kind of built into your tuition, so you've already paid for it. And you're welcome to visit us over here in the 2000 building. You're also welcome to go to other campuses. You live closer to another campus, or if you just want to check out another campus. Every campus has their own set of tutors and their own hours, things like that. So we pass that as schedule, that green thing that's got all the names of our tutors, the subjects they do, and the times they're available. And if you lose that, that one's specific to Brown Rock. So that's got myself and Trish listed on there for biology. But if you scan the QR code that you have, that other small piece of paper, that will take you to, all of these things for everyone.
Would you like one?
Also shows you who we have available for all you can do as well. So that's something that we're doing as well. Most of the important things. I might be forgetting some things. Anybody have any questions? Ah,
Did y'all cover serial and parallel dilutions over there? Is that
We
something you can
do.
help
we
students out
do.
with?
Do y'all
Okay.
do that? The all done.
Yeah, y'all need that for this Wednesday, yeah. They don't know it yet maybe, but they
Yeah,
might need
that
it.
can be tricky. So if you want to come in for that, I know you'll do that a lot in the labs. We can help you with that. Either of us can help you with that. And then we have other great people there too. So come in, we're open Monday through Thursday, 9 to 8. Friday, we close a little early. It seems like people don't like to study on Friday nights. And Saturday, we're open 12 to 6. Sunday, you can get help online, but you can also get help online other days. I know that's a lot of information really quickly. If you forget anything, that QR code, all this is online, everything where you can find all that.
It shows Friday that you're reading, is that? I'm not sure.
Yeah, no, that's right. Yeah, that means, so Friday, where are you looking? Yes, so I'm there Friday, 11 to 5. Under biology, you can see me there. Yeah, so the campus is open, or the learning lab is only open until 5 on Friday. You just don't come Friday night. And that's about all we have to listen.
Recording in progress.
Anything with the one that had-
It's a tough course, but we probably know that, my mom, you can save you time, if you're getting frustrated because something's not working for you. Don't get frustrated, come, fix and help. You know, the instructor can't be, have office hours 24/7, but we come pretty close. We can fill in the gaps.
Thank you so much.
Yeah.
Is there a way that, like, if I want to offer a bonus assignment where somebody could come spend an hour with y'all over there, is there a way to keep track of that pretty easily? Like they can
we
sign
probably
in or
figure it
something?
out.
Okay.
Yeah, do you wanna, I can leave my email with you and then you can.
Sure, okay,
you
yeah,
can email me.
We can have them fill out a form and we can sign on it, maybe.
that sounds good, okay,
Something
just a
like that.
note that says they came over there?
Yeah.
Okay, cool. Okay, so there it is, y'all heard it for the first time. Spend an hour in the learning lab, for the first time, not every time you go, but the first time you go, just so you can see what it's like, let's do, I don't know, 3 bonus points towards your lecture exam pool. That sounds fair.
Yeah.
Awesome. Okay, thanks so much, Nick. And
Yeah.
thank you too, Trish.
Yeah, see,
Really good stuff. Y'all do spreadsheet stuff too over there. I bet y'all can teach them how to do functions on spreadsheets.
do you?
We see lots of that, really.
Yeah.
Good, okay. Love it. Awesome. Thank you so much.
All right.
Have a good one. So many opportunities for extra credit in this class, man. You gotta take advantage of all of them. No, they're gonna be really helpful. You heard Trish, you know, if you're struggling in this class, there's just, you don't need to. You can just kind of go over there and struggle with somebody by your side and they can kind of help you out with stuff. I'm here for that too. Leo, your SI is here for that too. But yeah, just, you know, it's free. And I guess you technically kind of already paid for it, so it's over there. Yeah, check it out. Gotta see it once. Gotta go get those bonus points and just see it once. Once you've seen it the first time, you're probably gonna want to go back. So. Is anybody going to SI in here? Has anybody tried SI so far this semester? Okay, a couple of you have. I think Thursday at 7:30 is when the next one's gonna be, if I'm not mistaken. Yeah, look out for those. Those are bonus points for simply going, or, you know, also just great review too. Okay, so this is a weird first slide, but this is our water lecture. If you're out there surviving in the mountaintops or something, supposedly you can survive 3 minutes without air, 3 hours without shelter, if it's cold, 3 days without water, and 3 weeks without food. I'm into those survival shows and stuff like that. I'm into that kind of thing, so this is interesting to me. But there's this really uncomfortable one I just bumped into on Netflix called Outlast. I'm just not too sure how I feel about that one yet. Does anybody know what I'm talking about? You know what I'm talking about? Called Outlast. I don't know if I recommend it honestly yet. Anyway, so what did we do at the end of last time? Does anybody remember what we did at the very end of class last time?
Bonds and hydrogen bonds.
Yeah, we drew something on the board right here. Okay, well, what do we draw up here? 5 water molecules kind of in an X pattern, and they're hydrogen bonding with other water molecules. Okay, awesome. So at least 1 or 2 people remember that, okay. All right, so we're going to cover lots of different things today. We're going to cover water and a lot of the amazing properties that water has, but we're also going to dig into acids and bases and pH. Y'all remember acids and bases, what those are? Remember pH? Okay, we'll talk about that. Okay, so, I mean, water, it's everywhere. Makes up a lot of you, makes up a lot of me, makes up a lot of organisms. It's really special and it's crucial for life in all sorts of different ways because really just a few very straightforward reasons lead to everything else that's interesting about water. It's a polar molecule. Okay. It's a polar molecule. What does it mean that water is a polar molecule? Anybody know what that means? What does that mean? Water kind of looks like this. One side has sort of a different amount of charge on it than the other side, different kind of charge on the other side. How do we show that water has a different kind of charge on the oxygen side than it does on the hydrogen side? Yeah, lowercase deltas with a negative sign. Okay, so I'll put that over there. And then there's lowercase or deltas on the other side, which are showing it's positive on the other side. Does that kind of ring a bell to anybody? Okay, why is water like that? Why is that molecule like that? Why does it have the partial negative on this side of it? Because of electronegativity, yeah. Because of, is that what you're gonna say?
You can
Stuart?
say, yeah.
Okay, nice, nice. Because of electronegativity, because water is a very, 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 very. What is it, Muhammad? A very, 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 very something element. Electronegative element. Yeah, it's a very electronegative element. Yeah, it's oxygen. That's the one. Yeah, so that's why it's a polar molecule. Okay, that's the reason, because oxygen is very electronegative. And then everything else is the result of everything else about water just stems from that simple fact. Oxygen. Very, what? Very what? Electronegative. Okay, so electronegative, so what? What does that exactly mean? That means something, doesn't it, Alyssa? I mean, it's a word, it's a big fancy word, but what does that mean about oxygen? At the subatomic level, what does that mean? Or at the very, very small level? What do you think, Jade? Why? What? Interesting chain of words there. But yeah, it's just it's bringing in the electrons. It's holding onto the electrons more closely, and so the electrons, which are negatively charged, right? They just spend more time clustered over here by the oxygen, and less time over here by the hydrogen. This is just the way we represent this molecule. It's like a line that shows 2 electrons and 2 electrons here. But the electrons are just kind of moving around this entire thing. They're just spending more time over here. This is where they're spending more time. Because oxygen is very electronegative, it sucks them in, pulls them in and holds on to them more closely. And so that gives us a little bit of negativity over there. it's negative over there. Then you have electrons spending less time by the hydrogens. And then you have a polar molecule. Ta-da. That's it. Yeah, that's it. That's all there is to talk about. Everything else is just automatic from there. Okay. Water can form hydrogen bonds. Why can it form hydrogen bonds? Is it because it's a polar molecule? That's part of it for sure, yeah. Can form hydrogen bonds because if you have another water molecule that's next to it, the partial negative side of that one's going to be attracted to the partial positive side of the other one. Right, Kelsey? Right, yeah, okay. Yeah. Okay, so let's just do a little reviewing before we jump back in. Maybe we should have done this first before I do that big thing, but this is okay. Water, H2O. We got two H's, 1, 2, and we have 1 O. Okay, what holds the H together with the O? A certain type of bond. A bond where we're sharing electrons. Electrons are shared between the O and the H. What kind of bond is that? It's a covalent bond, yeah. What does it mean for a bond to be covalent? What does that mean at all?
It's sharing the electrons rather than swapping electrons, it's sharing the electrons, the valence electrons.
Thank you, Jason. Yeah, electrons are being shared instead of being given away from one group to another group or another atom to another atom. Exactly. So we have two covalent bonds right here and here. What do each of those covalent bonds represent? Like what, like there's a line there. I mean, sometimes it just looks more like this. What does that line mean? That line in between the O and the H. It means there's two electrons there. One line means two electrons. Exactly. Okay, so that's the way bonding works. You got to have two electrons for a bond. It's for a covalent bond. Okay. Now, because of water's structure, because this polar molecule that can form hydrogen bonds, it forms the hydrogen bonds because of the partials on one side versus the other side. You know that positive and negative are attracted to each other. You know this, right? So partial positive and partial negative are attracted to each other too. Right, Ashley? Yeah. Yeah, it's true. It's not just because I say it is. It's because it makes sense. This is a hydrogen bond here between these water molecules. Okay, well, you know, whatever, however I can get it, that's fine. Okay, so how do we feel when we see this? When we see that dotted line between the O and the H there, do we think to ourselves that doesn't mean anything? Or do we think to ourselves, oh, I think I kind of sort of get that. Kind of sort of can imagine what's going on there. Very, very small molecule, but it's attracted to another very, very, very small molecule. And everything else at the macroscopic level, when we look at our bottles of water and we look inside and we say, oh my gosh, that's just a bunch of those little things in there that are lining up this way. Some of the time. Okay, hydrogen bonds. Okay, moving to new material. Water, hydrogen bonds, but it exists in 3 different states based on really how warm or cold it is. Okay. Most of the time, well, I shouldn't say most of the time, but some of the time you're going to see water in its liquid state. And that's where water is just kind of moving around, water molecules moving around, bumping into other water molecules. And sometimes they're hydrogen bonding for a split second. Sometimes they're not. They're all just kind of transiently linking up and hooking to each other and moving along their way, flowing or just sitting there, moving around. Okay. What happens when you heat water up? What happens when you start to heat water up? Do these water molecules start moving around more slowly or more quickly when you start to heat water up? They're gonna start moving rapidly. They're gonna start just bouncing around like crazy, going everywhere. More and more energy put into the system. They're just kind of flying around, moving. And then eventually some of them escape. They escape the liquid water and they become this other thing that is no longer part of the liquid phase. It's the gas. They become the gas, okay? So when you heat water up enough, it's flying around the room, it's flying around above the surface that it came from, whatever. Gas is different from liquid water because there's no hydrogen bonds formed in gas. Got little molecules of water flying around. They don't have time to hook up with other water molecules. They just can't do it. They're flying, they're moving too fast. Gas molecules are moving around so fast. Hydrogen bonds are not formed in gas. What about when you cool water down? You bring it down real low temperature, and eventually at some specific temperature, it stops moving. What temperature is that? 32 degrees Fahrenheit? Okay, 32 degrees Fahrenheit, we get solid water. 32 degrees Fahrenheit, we get solid water, okay. So slow moving water is going to orient itself a specific way with respect to other slow moving water molecules until they stop moving. And when they stop moving, they're going to form that perfect 4 hydrogen bond thing that we all drew together last time at the end of class. And they're going to form this structure that is kind of like, it's like a crystal structure. It's the crystalline structure of water. And when you have water in that state, it kind of, it pops out a little bit. Because water molecules are not as close together in this state as they are in the liquid form. And what that means is that solid water weighs less than liquid water. Solid water weighs less than liquid water. Solid water just weighs less. So that means that it floats, right? It floats. It floats on liquid water because it weighs less. Okay, so that's why when you get this ice that forms, it kind of floats on the water. It doesn't sink to the bottom. Just that would be weird if it sank to the bottom because the water molecules are more spread out in ice than they are in liquid water. Does that kind of make sense? Yeah, okay, very good. And I mean, just think about if water did sink when it froze, what would happen? What would the world be like? What would happen if water sank when it froze? Yeah, I think so. I think they would freeze to death. It'd just be a bunch of frozen water that sinks to the bottom, and the top freezes, sinks to the bottom. Keeps sinking. All you have is ice in there eventually. Dang, how would life have even like been possible with water? If water were heavier than solid form than liquid form. And that's kind of strange too, because if you take, I don't know, like gold or silver or lead or something like that at the periodic table, you get the solid form of that and the liquid form of that thing, it's going to sink to the bottom. But water is unusual. Thank goodness it is unusual, because otherwise wouldn't have all these amazing properties that it has. Okay, so when it comes to some of the properties water has due to its polarity and due to its ability to form hydrogen bonds, it leads to this thing called specific heat. If something has a high specific heat, it basically means the same thing of it meaning having a high heat capacity. It just means it takes a lot of energy input, takes a lot of work, a lot of energy to make the thing heat up a little bit. Because water is kind of stuck to other water molecules. It's stuck. Okay? Well, it takes a long time for water to heat up. It takes a long time for water to cool down. Okay? Can anybody think of any? Actually, I think y'all can. I saw the discussion board posts. I saw them. So can you think of any example of water having a really high heat capacity or high specific heat, just in everyday life? No, you can. It's the question, are you gonna say it out loud in front of everybody? Y'all are really talking about the post on the discussion board. Yeah. Didn't you talk about air conditioning? I'm talking to you. Yeah, I'm talking to you. I'm talking to you, Veronica. Yeah.
I talked about, I don't even remember, yeah.
Oh, okay.
Being a solvent,
Okay.
other solutions.
Okay, fair enough. All right, we'll get it. We're gonna get to you then. We're gonna get, well, that's coming up soon. I think like 75% of y'all talked about high heat capacity though. Nobody wants to say anything about that? What's it like to live? Has anybody been to California before? Anybody like the coastal areas of California? Okay. Okay, I mean, California is going through a real rough patch right now for all sorts of other reasons, but in general, the climate there is pretty temperate. It's because the Pacific Ocean is this big body of water that can absorb a lot of heat, can absorb a lot of heat energy. And so that makes things kind of cooler in the summertime. And it can also release a lot of heat energy, or slowly release heat energy when it's in the wintertime. So it's just being next to the coast in California, just got this big body of just stuff that's holding on to temperate weather, basically, temperature. What about sweating? I think we all talked about sweating. Yeah. What about, well, I guess we'll get to sweating. It's related. It's related. It's the heat of vaporization. It's the same thing. It takes a lot of energy to heat water up. It also takes a lot of energy to get water to turn from a liquid into a gas. It takes a lot of energy to do that. So that's the high heat of vaporization. It's because water molecules are stuck to each other. Water molecules are stuck to other water molecules because they form, what do they form, Devin? Hydrogen bonds with each other, because they form hydrogen bonds with each other. Right? Right, guys? Right? Okay. So water has a high heat of vaporization, has a high specific heat, has a high heat capacity. That's because all the water molecules are stuck to each other. They don't want to be agitated and moved and, escaping the liquid. They don't really want to do that. They don't want to move around that much. They want to stick to other water molecules. And that's kind of what they're doing most of the time. So another thing about water, based on its polarity and its ability to form hydrogen bonds, leads to this water being the universal solvent. Water can dissolve just about anything. Anything, well, there's exceptions, of course, but water can dissolve a lot of things. So now I'm ready for you, Veronica. I want you to say whatever you want about water being the universal solvent.
Well, you could, my example was you could dissolve stuff with it. Or make things like less concentrated.
Okay. Oh yeah, you're talking about your electrolyte drinks, weren't you?
Yes.
Yeah, I remember that. Okay.
This thing blue.
Oh,
Yeah.
okay.
Out here.
Gotcha. So what's your electrolytes that's going on?
Oh. It's something that's supposed to calm you up.
Okay. Oh, you're gonna get pumped up and get electrolytes. Nice. Okay. Who doesn't want that? Awesome. Okay, good. Yeah, so water is the universal solvent, right? It dissolves things. So you can like mix sugar with water and it like kind of gets hidden in there. And dissolve salt in water, it kind of gets hidden in there too. Why does that happen? Have you ever thought what is sugar? What's the name of sugar? Sucrose. Yeah, sucrose is just table sugar. It's these little white crystals here. Those are sucrose. I don't know if anybody's out there having, a cup of tea, a little tea party with little sugar cubes in it, but this is, you know what they are, right? You get table sugar. So look at the sucrose molecule right here at the molecular level. Why is that sucrose molecule able to be dissolved in water, do you think? Kind of look at it. I put the lowercase deltas on there. That should help out a little bit. Why do you think that can be dissolved in water? The water cloaks it. It just kind of surrounds it and it hydrogen bonds in a specific way with it to where now there's like a sphere of water around all the little sucrose molecules. And so that's what dissolving really is. They're hidden by water. You ever like dissolve something in water and then you can see the little crystals at the bottom and then you couldn't, and then you kind of look at it and it kind of has this like sheen, this kind of like this weird sort of look. Well, if you haven't, do that sometime. Yeah, so this is also a slide to introduce words like dissolve. So dissolve is when the things get hidden in the water because you mix them in. The solvent is the thing that dissolves the solute. And in the solute in this case would be, what is the solute in this case? We're dissolving these cubes in the tea here. What is the solvent? What is the solute, excuse me? Sugar, yeah, sucrose or sugar. Yeah, that's the one. Okay, and this works with other things too. This is what is this? Sodium chloride. Sodium chloride. You heard of sodium chloride before? Yeah, salt, table salt. It tastes good. Salt and sugar on your stuff. Okay. I mean, so it's the same kind of thing that's going on here. You got a positively charged sodium. It gets ripped off of this, this block of salt because it's ionic. Gonna have little positive sodiums and little negative chlorides kind of floating around that can be ripped off. And water is just going to orient itself. The positive side of water is going to orient itself towards the negative chloride, and the negative side of water is going to orient itself towards the positive sodium, right? Right? Right, guys? Right? Yes. So water is just surrounding things, and that's how water dissolves things. There's a subtle distinction between dissociation and dissolving, but I'm not going to get into that right now. In case anybody's checking me, like, is he going to say it? Is he going to talk about that? Not yet. Maybe not ever. I don't know. Maybe we'll come back to that. Okay, so more unique properties of water. This is all, again, due to two major things about water to start off with. What are the two things about water that basically lead to all these other properties? Two things. We talked about them like on the first slide. We spent a lot of time there. Had to be worth it for something, right? Polar molecule. And it can form hydrogen bonds. Yes. Okay, so that leads to cohesion and adhesion. Cohesion. Cohesion is just when water sticks to other water molecules. Water sticks to other water molecules. So it's important when you think about how water gets from the soil and the roots where for trees or plants or anything out there, it wouldn't be able to get up to the top leaves and all through the rest of the plant and every part up here if water didn't stick to other water molecules. That's one major component of this. Okay. So cohesion, water sticking to other water molecules. This is a little long cell inside this tree here. Okay, they're sticking together. But you also have to have this other thing working called adhesion. Adhesion is when water sticks to other things that are not water because of its ability to form hydrogen bonds. So that's our adhesion right here. Water sticking to the side of this plant. Okay. So water just keeps evaporating from the top leaves and it keeps being dragged up from other water molecules, pulling it up from the bottom, sticking to the sides of the cells as it climbs its way up. And then it evaporates off the top and it keeps dragging other water molecules up. So this is how water gets from the soil all the way up to the top. That's it. That's it. That's how water gets it up there, is by cohesion and adhesion. All because what, Kelsey? Water can do what? Water's what? Water can form hydrogen bonds. That leads to all this. Yeah, water's polar, it can form hydrogen bonds. That's everything. Okay, cohesion's kind of cool because it also allows for the development of something called surface tension. If you try to like take a pin and stick it on top of water and try and not let it sink to the bottom of the water, it's possible. It's possible if you place it carefully enough. It's just there's this tension that is formed because the water wants to stick to the water molecules so tightly that the pin placed properly can't break through that. Amazing. It also allows you to do things like this. You ever taken a glass of water and just tried to pour it up as full as you possibly could until it just bulges out over the sides and doesn't quite run over the edges? Basically every weekend, that's what I'm doing most of the time. It's a Friday night. What else are you gonna do? You don't got anything else to do? You're gonna fill up glasses of water. And then if you're feeling really good, if you're feeling really excited, you want to do something special occasion, get out your pennies, start putting drops on those until eventually it just, oh, this is so much fun. It's because all the water molecules are just kind of stuck to other water molecules. That's why droplets look the way that they do. They're not flat. they're forming these domes everywhere because water's sticking to other water molecules. Yeah. Should have brought some glasses in here. There's some pennies. Everybody has a water bottle. We could have done this. We could have made this happen.
You know, like one of those games, you've seen, videos of people who will go around in line and they'll take they'll all like put the maximum amount they want. And then let the person challenge it to see if like they can still put more dots, and the person who like puts the last dot and it all just bursts.
Oh, okay. That'd be a nice way to do it all together. Yeah. Just have one glass or one penny. We all come by with one drop.
Yeah, but the thing is, the first person can put a lot, like a lot,
Oh, okay,
so they
okay.
can sabotage.
Dang, okay.
So it just depends on who's putting it.
Okay, okay. I'll have to think more about that. To come up with some activity together. So surface tension also allows for some interesting organisms to walk on water. Like there's bugs that just kind of sit there, water striders. You got this lizard. You've seen them on, maybe you haven't, but I don't know. Maybe you've seen them on one of Attenborough's programs, just running across the lake, the basilisk lizard. Yeah, they wouldn't be able to do that if water didn't have all the surface tension. There's cohesive properties. Oh, and this is my favorite video of all time. You seen this one, Corbin? Okay, don't spoil the surprise. This guy's in outer space.
Okay, so here's a soaking wet washcloth. Get the microphone so you can hear me while I'm talking. And now let's start wringing it out. It's really wet. It's becoming a tube of water. The water is all over my hands. In fact, it rings out of the cloth into my hands. And if I let go of the cloth carefully, the water sort of has it stick to my hand. Okay, so the experiment worked beautifully. And the answer to the question is the water squeezes out of the cloth. And then because of the surface tension of the water, it actually runs along the surface of the cloth and then up into my hand, almost like you had Jello on your hands or gel on your hand, and it'll just stay there. Wonderful moisturizer in my hands. And the cloth doesn't really unravel itself. It just stays there floating like a dog's chew toy, soaking wet.
All right, that you can't forget what cohesion is and surface tension is. If you just think about that guy, the water's stuck to his hands. It's amazing. That's it. That's my favorite. That's the best video on YouTube. Spread the word. All right. So adhesion. How's adhesion different from cohesion? I guess we've already kind of talked about this, but how's adhesion different from cohesion? What is cohesion? Maybe we should start there. What is cohesion? Water sticks to water, yes. Cooperation, cohesion, water sticks to water. Adhesion. How's adhesion different from cohesion? Water sticks to something else, yeah. So when you stick a tube, maybe like a glass tube in water, it crawls up the sides of the tube and all up in it because of capillary action, basically because of adhesion. It's the same kind of thing. Why is there why does water kind of, turn up at the edges of glassware? That's also because of adhesion. Why do we have to look for the meniscus when we're looking at anything to see how much we're measuring? Because everything's designed that way based on the knowledge that adhesion is a thing. Okay? Adhesion allows for water to travel up through the roots of plants to the top parts of things as well. But also you can just stick a glass tube in water and watch it happen. The glass tube's at. Okay, so we'll watch this video.
Water. It's all around us. Makes up 70% of the Earth's surface and about 60% of your body. Let's start with the basics. Water is a colourless and transparent substance. When it is pure, it has no smell and no taste. If you've ever thought that one type of tap water tastes different to another, you're not wrong. Tap water in different areas may have slight impurities from various metal ions. Water is a liquid at room temperature. It freezes at 0 degrees and boils at 100 degrees at standard pressure. But have you ever wondered why the boiling point of water is higher than, for example, methanol? Well, you might know from this video that water is a polar molecule with slightly positively charged hydrogens and slightly negative oxygens. Imagine a bunch of water molecules in a beaker. They are in liquid form, so can move around each other, but the delta positive hydrogens from one molecule are weakly attracted to the delta negative oxygen of another. This is a type of intermolecular force, and it has a special name, hydrogen bonding. Because of this, the water molecules need quite a bit of energy to overcome the hydrogen bonds and escape from the beaker as a gas. Water is a very good polar solvent, so good it's often called the universal solvent. That's a bit of an exaggeration, but it's certainly true that many common chemical compounds will dissolve in water. Here's just a few: hydrochloric acid and many other acids, sodium hydroxide along with other bases, soluble salts such as table salt, sodium chloride, and sugars. Here's a challenge though. Can you think of a large and important type of compound that won't dissolve in water and instead floats on its surface? More importantly, can you think why they do this? Pause the video, think carefully, and resume when you've got the answer. Well, the answer is lipids, or in plain English, oils or fats. They don't dissolve in water because they're non-polar and therefore hydrophobic, meaning they don't like mixing with water. One of the most unusual qualities of water is that it can act as either an acid or a base. A water molecule can either accept a proton and become a hydronium ion with a +1 charge, or donate a proton and become a hydroxide ion with a -1 charge. This is one of the reasons why water is so useful in all sorts of organic chemistry reactions.
Okay, so I took the next step there at the end of the video. We're gonna talk about some of that stuff too. But yeah, hopefully is that helpful to watch those videos after we talk about stuff? Is that kind of like tie things together for y'all a little bit? Maybe you like the videos? Okay, seeing some nods and some blank stares, but that's all right. Okay, so acids and bases is now what we need to talk about. My main goal in this whole chunk is to get you to understand what pH really is, 0 through 14. And also to get you to know when you hear about an acid, what do we know for sure that we're talking about? Hear about a base, what do we know for sure we're talking about? Some properties of these things. Okay. So presumably y'all have heard of acids and bases before, right? Okay. So acids are typically things that have a pH. Actually, no, I'm jumping too far. For anybody that's not super familiar with acids and bases, I'm jumping too fast. But acids are typically things like lemon juice and, orange juice and coffee and stomach acid. Bananas. Didn't think bananas were going to be that acidic, but according to this thing, they are. Okay, and then bases are kind of on the other end. They're more alkaline, or they have a different sort of, lots of household cleaners are bases. And then some waters are alkaline or basic as well. Acids and bases. So before we jump into acids and bases, I want to talk about water. Water can dissociate. Water can come apart. And when water does come apart, it becomes two different things. It becomes the OH minus and becomes the H plus. What is OH minus? There's another word we could use instead of OH minus for this. Was it? Hydroxide. Hydroxide. OH minus is hydroxide. Is hydroxide an anion or a cation? Anion? Yeah, it is. Why is it an anion? Because it's negative. Yeah, you got it. We had the onion discussion last time. Onions are negative. Okay, and the H plus, what do you call the H plus here? A cation, or just, yeah. We call it the hydrogen ion. Which is positive, so it's a cation, yep. Absolutely. Have you ever thought about, well, we're gonna get to it. Have you ever thought about what hydrogen is all by itself, just the hydrogen atom? A hydrogen atom has one electron and one proton, it doesn't have any neutrons. That's what most hydrogen is. And so if you take the hydrogen atom and you get rid of the electron, what are you left with? What are you left with when you get rid of the electron there? You no longer have a hydrogen atom. You have a hydrogen ion, and a hydrogen ion is simply just a proton, simply just the centerpiece. We have H plus. H plus, we have one proton. So sometimes when I refer to the hydrogen ion, I might just call it a proton. Sometimes I might call it the hydrogen ion. Sometimes I might even go the extra mile and call it the hydrogen cation. But I'm talking about the same thing with all these, and none of those are hydrogen atoms. They're different. Okay. Oh, there it is. Hydrogen ion, hydrogen cation, proton. Ways to name the H plus. Okay, so when it comes to acids, an acid is simply some molecule that can donate H plus. Simply a molecule that can give away an H plus, and give something like that away. When you put an acid in a solution, it's going to increase the H plus that exists in that solution. So it's going to increase the hydrogen ions or the protons in that solution. And if we're talking about an acidic solution, we're talking about a solution that has a high concentration of H plus. Okay. So really every way to come at this, we're coming at it here. The other thing to note about acids is based on how much H plus they have, they can be considered strong or weak. Strong or weak. So what do you think, Ava? Do you think that a strong acid is going to have a lot of H plus or a little bit of H plus? It's going to have a lot of H plus, yeah. So a strong acid is going to have lots of H plus. What do you think, Cynthia? Are weak acids going to have a little bit of H plus or a lot of H plus? A little bit of H plus, yeah. Okay, so that's what we know so far about acids. So what I have over here is on the right side of the screen, we have hydrochloric acid being represented by these balls. And when you stick them in water, the balls come apart. And what that means is they're dissociating in water. Water is pulling them apart, they're going to dissociate. And when they dissociate, all the hydrochloric acid is going to become these two things. It's going to become H pluses for these half moons that are kind of pink. And it's going to become these Cl minuses, which are chloride ions. Okay. So adding that to water, did that increase the H plus concentration? Yeah, like every single hydrochloric acid molecule is added to that, added an H plus to it. So presumably we're gonna add more than 3, but we're gonna add quite a bit of H plus by adding this to water because it dissociates when you put it in water. It comes apart. Hydrochloric acid is gonna come apart, gonna add some H pluses to this. Okay. Does anybody know what these brackets around the H plus mean there, right there? What does that mean? Anybody in chemistry right now? What do the brackets around the H plus mean there? No? Okay. So the brackets around the H plus is just a simplified way of saying concentration. Okay, so the concentration of H plus is increased there. You knew that, didn't you, Karthik? You did. It looked like you knew that back there. Too shy. That's okay. So there's just examples of strong acids. These are all strong acids here. Hydrochloric acid. When you put that in water, you get a bunch of H plus. Sulfuric acid. When you put that in water, you get a bunch of H pluses. Nitric acid, put that in water, a bunch of H pluses. Yeah, so those are strong acids. Weak acids, like this one up here in the upper right is called carbonic acid. I don't care if you know that specifically, but that's what it's called. You add that to water. It's going to add some H plus. But it looks like some of them still kind of stay together. Some of the carbonic acid molecules are still whole and they don't come apart. Okay, so any molecule that does that when you stick it in water, we say that they're partially dissociating in water. They're not completely dissociating because they don't all get ripped apart. Okay, so they're going to increase the H plus in the solution, but not a lot. And so that's what a weak acid does. Increases the H plus concentration somewhat, weak. Okay, so carbonic acid is an example of that. Carbonic acid is all up in your blood. You've thought about that before. Maybe some of you all have taken A&P in high school and you know what I'm talking about there. If not, that's okay. Also acetic acid. Where do you find acetic acid? Or what is acetic acid? What's like the common name for acetic acid? Anybody know? Vinegar, yeah. Vinegar is acetic acid. So those are both weak acids. You know, they're going to increase the H plus concentration, but not by a ton, just by a little bit. They're going to increase the H plus here when you put them in water because they dissociate, because the acid dissociates. All right, strong bases are kind of similar to strong acids, but like we're not talking about H plus concentration increasing anymore. We're talking about something different. Strong bases like sodium hydroxide, sodium OH, NaOH. When you stick them in water, they completely dissociate. They completely come apart. But this time, what's being added to the solution here is a bunch of OH minuses. OH minus, OH minus, OH minus, OH minus. Was it you, Kelsey, that told me what that was? Maybe it wasn't you.
I'm sorry.
That's fine. That's fine. That's fine. That's fine. No harm. Somebody told me what the OH stood for. Oh, maybe it was Anthony. The hydroxide. We got a bunch of hydroxide that's been added there. We can call it OH minus. That's fine too. Okay. So adding this sodium hydroxide to water makes it dissociate. It's going to actually decrease the H plus in the solution. So it's going to do that. Or sometimes increase the hydroxide concentration significantly. You know, if you just take a moment to think about why this would be the case, it kind of makes sense. How is it going to decrease H plus concentration? How is OH minus going to decrease H plus concentration? Yeah, they kind of cancel each other out because the H plus is going to come together with the OH minus. They're going to form, what are they going to form, Sean? No, not really. Yeah, they're gonna form a water molecule. Yeah. No, good answer. Good answer in general, though. No, good answer in general. Yeah, it was a safe bet for sure. Yeah. Okay, so some examples of strong bases that when you stick them in water, they fully dissociate into hydroxide, adding a bunch of hydroxide to the solution, are sodium hydroxide and potassium hydroxide. Okay. Very strong. We'll be dealing with sodium hydroxide in the lab a little bit. Not this week, but next week. Weak bases, they partially dissociate. So you get some hydroxide so this is NaOH, oh, sorry, ammonia that's being added to the water here, excuse me. And that's going to give us some OH minus. It's gonna decrease the H plus concentration in there because it's gonna pick up some H pluses. And it's gonna increase the OH minus also, but just a little bit. So ammonia does this, and the carbonate ion does this as well. Okay. Weak bases, they're weak. Oh, whoa. If you. Oh, never mind. I thought I was going somewhere else with that. An example of a neutral solution that is neither acidic nor basic is just pure water, pure deionized water from the lab. You know, the spigot out in the lab that has the pure deionized water, or just salt water, sodium chloride water, not from the ocean, not from the ocean. If you get it from the ocean, it's different. But as long as you got concentrations of H plus and OH minus equal, that means you have a neutral solution. And where we're headed from here is talking about pH, okay? If something is neutral, it has a pH of 7. So that's kind of the middle of the scale, the pH scale is right in the middle with the 7. Has anybody heard about that before? pH of 7 is neutral? Okay. Yes. Phew. Okay. Okay, so this is a pH scale. This is one representation of it. I like this one because it shows the numbers of the pH scale, which seems important. So we got 0 down here, and we got 14 up here, and we got 7, which is right in the middle. Okay. So what do we know about a pH of 7 so far? What do we know about that? Neutral. Okay. What does it mean for a pH to be neutral, though? What is it? It's at a safe level. Okay. Yeah, I'm with you. It's neutral, so like it's not going to be corrosive, probably. It's not going to eat away, not going to damage anything. Okay, yeah, I agree with that. Nice. What is the concentration of ions that we're going to find in something that has a pH of 7? What's the ion concentration going to be in there? And what ions are going to be? We like just talked about it in the previous slide. Thank you, Alyssa. That's what I'm going for here. Yeah, so basically pH 7 means we have an equal number of hydrogen ions and hydroxide ions. And if you count up these dots here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's gonna be 10 red dots there and 10 blue dots. Okay, same number of hydroxide and hydrogen ions in this solution. So we got a neutral solution. What if we go in the acidic direction? What if we go very far in the acidic direction? If something is an acid, it's going to have a low pH below 7. So we're talking about in this zone from like 0 to 6. If we go all the way down here to whatever this is, maybe like 1.5 pH, we have a lot of hydrogen ions in like just one hydroxide ion, at least represented as this way on this diagram. Just one hydroxide ion, but bunches and bunches and bunches of hydrogen ions, okay? Now that, I would say, is not safe. That's not safe. You don't want to dip your finger in that. That's not good. You don't want to drink that either. None of those things, okay? But if I go the other direction, if I go up on the other side, I shouldn't cross that out. Alkaline. What's another word for alkaline? Does anybody know what the other word is for alkaline? Basic. Okay, basic and alkaline on the other side. If we go all the way up to maybe like pH of 12.5 or something like that, what's the major difference that's going on up at 12.5 over here? Just speaking of hydrogen ions, let's focus on the hydrogen ions. Alyssa, you can tell us again if you want to. Yeah, there's very little hydrogen there. Yeah, there's one hydrogen. So there's very little hydrogen over here, but there's lots of hydroxide, okay? So you really can think about the pH scale in terms of hydrogen ions or hydroxide ions if you want to. And if you take chemistry which many, chemistry 2, I guess, is when you're really gonna get into that. You'll talk about the pH scale. There's the pH scale and there's the pOH scale. You can be talking about either one and deal with that, deal with all the fun that comes with that. But for now, just think of lots of hydrogen ions, low pH. Few hydrogen ions, high pH. Just simplify. Simplify it. And sometimes that's tough to just like really wrap your mind around. A low value, a low number in the pH scale is a lot of hydrogen ions. If you haven't heard that enough times in your life, you might just not really get that, but it's true. Just a low number means lots of hydrogen ions. Okay, so the pH scale is really useful. Instead of just talking about concentration of hydrogen ions, because we'd have to do a lot of calculations to make that work. So another way to just simplify is to use the pH scale. And basically, when you go from one value to another value in the pH scale, when you go from 7 to 6, or 6 to 5, or 5 to 4, 3 to 2, or something like that, when you change one value, it represents a 10-fold change in the number of hydrogen ions. Every value you shift, one value, 10 times as many hydrogen ions, or 10 times fewer hydrogen ions. Every time you move one pH value down, every time I go from, let's say, 6 to 5, I'm getting 10 times more acidic. So something with a pH 5 is 10 times as acidic, 10 times more acidic, however you want to say it, than something with a pH of 6. So pH 5 is 10 times more acidic. 10 times. What about if I move up a pH value? Can somebody give me the opposite of this? What if I move up one pH value? What would be the other thing that would be possible here? 10 times more basic. Okay, 10 times more basic. Absolutely. So if I say go from pH 8 to pH 9, 10 times more basic. Or 1/10 as acidic. That kind of makes sense too. 1/10 as acidic. Okay. We could do either one there. And basically the pH scale is on a negative log base 10 scale. So what that means is every time you shift a value, you're just shifting by a factor of 10 every time. Okay, so just officially, this is what's true. But I like looking at it just kind of on the far right of this diagram. I think there's a lot of juicy information over here. Let's look at something with a pH of 5. It has 0.00001 concentration of hydrogen ions. Okay, that's a pretty small number, it sounds like, right? But it's actually not. It's actually quite a bit. Anyway, is this number 0.0001 hydrogen ions bigger than the other value, or is it smaller? It's bigger, yeah, because there's fewer zeros. Yeah, it's a bigger number. In fact, it's 10 times as big. It's 10 times bigger. Okay. You go all the way down here to pH of 14, you have 0.01, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 zeros and a 1 there. So basically just moving the decimal point over 14 times if you come from the other side. That's less hydrogen ions. That's way less. Okay. So all this is based on the number of hydrogen ions. Okay. You okay with that? You okay with that? Yeah. I gotta start calling on y'all. I gotta start learning everybody's name in here. All right, so here's an example we can work through together. How would you describe how would you describe pH 2 compared to something with pH 4? How much more acidic is something with a pH 2 compared to something with a pH 4? And don't just give me the answer, walk me through how I'd do it. How would I determine that? You want to help us? Sorry, I didn't mean to cut you off there.
The 3 would be a 10, and then the 4 would be a 100. So, well, not 20.
No, I see where you're coming with that. But we gotta be careful, yeah, it's gonna be 100 times. No, it's fine, it's fine. It's okay, totally fine. But y'all see that, what he did there, it's gonna be, we moved from 4 to 3, which is gonna be 10 times more acidic. Move from 3 to 2, it's gonna be 10 times more acidic. And 10 times 10 is what? It's 100, yeah, so that's gonna be 100 times more acidic. Or if you just wanted to just count how many values is different, it's 10 to the second power. 10 to the second power more acidic, which is the same thing as 10 times 10. Okay, so it's 100 times more acidic. A solution with pH 2 is 100 times more acidic than a solution with pH 4. All right, so if that's the case, Bernadette, you up for this?
Yeah.
Was that a yes or an emphatic no? Yes, okay, awesome. How would I describe pH 10 with respect to pH 13?
But I would consider it 1,000 times more acidic. Because whenever you're moving 1 to 3 to some, I mean, not decimal, but 3 places, I do with the power, so it'll be 10 to the 10 cube.
Mhm.
10 cube is 1,000. So it would just be 1,000 times more acidic.
Yeah, that's exactly right. Yeah, so basically 12 is 10 times more acidic than 13. 11 is 10 times more acidic than pH 12. And 10 is 10 times more acidic than pH 11. So 10 times 10 times 10. Is that, you agree with that? Yeah, so you went 10 to the third power, which I agree with. Equals 1,000 times, 1,000 times more acidic. Okay. Would it also make sense to say 1/1000th is basic? Can y'all imagine that too? Is that gonna make sense too? You like that? Yeah.
There be certain speakers where they understand like 1/1000 as basic versus 1,000 times more acidic.
I mean, it's good to keep those facts straight in your head for sure. Yeah, it'd be good to be able to realize that, absolutely, yeah. Yeah. Because yeah. Absolutely, yeah, we want to know which direction we're going. We also want to just wrap our minds around the fact that high pH values, if we're moving up, that's going to be more basic, or it's going to be less acidic. And if we can use all those verbs or those words together in our mind, that's going to be useful for sure. How's everybody feel about that? Because this is something that we're all going to need to be able to do eventually. We need to be able to count 1, 2, 3, 4, and kind of, I guess, okay, so the rule of pH questions is that if you ever have something that is not a factor of 10 in your answer, you went wrong somewhere, okay? So if you end up with something being like, 200 times as acidic, we're not going to be dealing with that, okay? 10 times as acidic, or 1,000 times as acidic, or 1/1000th as acidic. Just depends on how many values you're going over. That's all that matters. Okay, this is another thing that kind of, I guess, shows pretty well how we use the pH scale. So if we have a solution with a concentration of 0.01 big M hydrogen ions, we write that as H+ concentration, is 10 to the third, negative third power big M? Ooh, big M. What's the big M? Yes, molar. Molar, yeah. What does big M stand for? Almost. It's a measure of concentration, so it's moles per something. Per liter, moles per liter. Okay. So when we think about those numbers in terms of, we're talking about a mole of them, it kind of makes us think, oh, that's actually a lot of hydrogen ions. It's not just some small number of hydrogen ions. Because even though it's a decimal point, a mole is a big number, is it not? How big's a mole?
10 to the negative 23rd, right?
Yeah, that's basically exactly right. Yeah. It's a big number. Yeah. Yeah, so big. I love how you said it like you weren't too sure, but you said the exact number. But I hear you. Yeah, it's funny. Yeah, it's great. Oh, there it is. Yeah. So I mean, basically, just in common language, like 6 sextillion or something like that. Common language. Is that a common word that I don't even know what that means? Sextillion. That's a big number. I think that's what it is. I think I've gone through this before and determined that's what it is. Anyway, so the point of this slide is to show you how simply you can figure out if something has a hydrogen ion concentration of 10 to the negative 8 molar, that's the same thing as saying that it has a pH of 8. It has a pH of 8. Very straightforward. If something has 10 to the negative 3 molar, it has a pH of 3. That's just what that means. It's like super convenient when you think about it like that. Just a super easy transition there. Okay, so let's do one more here. Let's compare 3 and 8. Anthony, you want to take this one? Okay, that's fine. Who wants to take this one? How much more acidic is pH 3 compared to pH 8? Ava, you got this? Yasmin? Jasmine? Okay, 100,000, let's see. 1, 2, 3, 4, 5 units over. Okay. So would this be 10 to the what power? 10 to the 5th power. Okay, so we do 10 to the 5th power. Sorry, that's pretty bad. It's gonna be that's gonna be 100,000. Yeah, you're right. I was about to like break the bad news to you, but you're right. Yeah. Yeah, just to check, because apparently I don't know what I'm doing. Yeah. Yep, it's gonna be 100,000. 100. So something with a pH of 3 is 100,000 times more acidic than something with a pH of 8. Is something with a pH of 8, how do we describe pH of 8 with respect to pH of 3? 2 different ways you could probably do this if you wanted to. What do you think, Peyton? Well, we're going in the higher way. We don't want to say neutral because you can't be more neutral. I mean, I hear what you're saying because we're going up that direction. But yeah, we're always going acidic or basics. Yeah. So say it again one more time. It would be 1/100,000th as acidic, but it would be 100,000 times more basic, right? If we're going up there. I'm sorry, no. Dang. You caught me. Yeah, okay. So you said exactly right the first time. We're going from pH 3 to pH 8. 1, 2, 3, 4, 5. We're getting 100,000 times as basic. No. 1/100,000. 1/100,000 times 1/100,000 times as basic. . right?
basic, but it's getting a smaller amount of basic.
I've messed this up twice, I think now, actually.
That's 3 to 8.
So, okay, so this is the solution, okay. If we're going from 8 to 3, if we're saying 3 with respect to 8, 3 is way more acidic than 8. So 3 is gonna be 100,000 times as acidic as 8. That's right, yes, I'm confident about that. Okay. But if we say this in another way, we could say that, and this is what you were trying to say, that 3 is 1/100,000 as basic as pH 8. Okay. Well, we could also, maybe we should just leave it there. Leave it there. If we want to go the other direction, we could. If we want to say, well, how much different is 8 compared to 3? We could say that 8 is actually 100,000 times more basic than pH 3. Or 100,000 as acidic as pH 3. We okay there? Okay. Did I confuse anybody? Is everybody just completely lost now? Completely lost?
I like how the basic basically looks like brown and messed up.
I don't even see it, but I wish I saw it. I wish I saw it. Okay, I'm gonna take your word for that. Okay.
When water dissociates, it breaks apart into an equal number of hydrogen ions and hydroxide ions. In contrast, when other substances dissociate, they may release more hydrogen ions or more hydroxide ions. For example, hydrochloric acid releases more hydrogen ions as it dissociates, and sodium hydroxide releases more hydroxide ions. Depending on its concentration of hydrogen ions versus hydroxide ions, a substance can be classified as either an acid or a base. The pH scale measures how acidic or how basic a substance is. It ranges from 0 to 14, with 7 being neutral. When a substance has a pH of 7, like water does, it releases an equal concentration of hydrogen and hydroxide ions. When a substance has a pH of greater than 7, it's classified as a base and releases a greater concentration of hydroxide ions. The more hydroxide ions that are released, the more basic the substance is. Bases tend to feel slippery and are often used as household cleaners. Milk of magnesia and ammonia are both common bases. When a substance has a pH of less than 7, it's classified as an acid and releases a greater concentration of hydrogen ions. The more hydrogen ions that are released, the more acidic the substance. Acids tend to taste sour. Lemon juice, stomach acid, and coffee are all examples of acids.
All right. Has anybody had ceviche before? You like ceviche? It's pretty good. It's like basically put lots of lemon juice and maybe some habanero peppers mixed in there or something spicy on some raw fish. And it kind of changes the texture of it. You know, it kind of it flavors it, but also makes it it cooks the fish with air quotes. Because it's not cooking the fish, but it changes the texture of it. In a similar way that cooking does change the texture of fish when you cook it, but doesn't have the same food safety implications, just for the record. But why does it change the texture of it? It's because of proteins that exist. You have proteins that exist, and the fish is basically a lot of protein. There's some other stuff in there too. And you put acid on protein, it makes the protein come apart, kind of. It makes the protein kind of fold in a different way, or it makes it denature. Okay, denature is the word here we want to know about. And we're going to talk more about macromolecules like proteins and other macromolecules like later, I guess, a couple lectures from now. But for now, yeah, putting acid on fish. That is a pretty common Peruvian dish. Does anybody know any places to get some good ceviche around here? Is that thing? Bernadette, you know?
But there's one there, it's called Ceviche 105.
Okay, ceviche 105. Okay, okay.
I think there's one downtown Round Rock, I think there's a.
Oh, yeah, okay. Oh, okay. Okay.
Good.
All right. Well, that's where I'm headed. After I get done filling up glasses of water on Friday night, I'll see y'all there. All right, so just another couple loose ends to tie up here. Buffers. Buffers are we're gonna be dealing with buffers in the lab, not this week, but next week. And basically buffers, when you have them in a system, they make pH not change as rapidly. If you add a bunch of acid to a buffered system, where it would normally change a lot, add a bunch of hydrogen ions, it doesn't in a buffered system. It really kind of absorbs that change that was gonna happen. So I think of buffers kind of like sponges. They absorb hydrogen ions when they need to, resist the change of pH maybe decreasing, or they release hydrogen ions when we're trying to make the pH of something not increase, not decrease too much. So basically it's just they act like a sponge. That's the way I think of buffers at least. So here's an example. We're taking hydrochloric acid, we're sticking it into an unbuffered system. We know hydrochloric acid's strong, it's going to come completely apart, add lots of hydrogen ions to the solution. Okay. But if we get a significant increase in H+ concentration, which equates to a big drop in pH. Low pH, lots of hydrogen ions. If we have a buffered system, this is a buffered system here, add the H hydrochloric acid to that, the strong acid. In this case, what ends up happening is you get one H+ that's added and increases the H+ maybe a little bit, but like in slightly dropping the pH, but not nearly as much as what would happen if the buffer wasn't there. Okay, so we'll see an example of that. We'll be working with buffers in the lab, not this Wednesday, but next Wednesday. Okay, you also have this in your blood. You know, carbon dioxide and water, basically, when there's enough carbon dioxide, you're going to start forming carbonic acid in your blood, which then can become the bicarbonate ion and the H+ ion. I don't actually, this is something you can go into much greater detail in you take anatomy and physiology, but the general gist of this is you're going to be making more carbonic acid or more bicarbonate ion based on the needs of your blood. Because you got to keep your blood at some kind of balanced pH value. If it gets too acidic, that's not good. So the buffer is going to hold on to some of the hydrogen ions like a sponge. They're going to scoop them up, and we're going to get more of the carbonic acid made, which sounds counterintuitive, but that's what happens. And then the opposite happens if your blood gets too basic. Maybe you drank some ammonia by accident. Ugh. You're gonna try and balance that out by releasing some hydrogen ions. Okay. That's generally how it works there. Does that sound right, Devin? Okay. You looked like you were trying to signal me that you wanted to comment. Okay, no. All right, so that's what we got going on there. And then neutralization reactions are also a thing where you mix acids and bases together in equal quantities. You end up with a neutralization reaction. Basically, the H+ mixes with the OH- and you get H2O. And so antacids, maybe you've taken antacids before, those are going to neutralize the stomach acid that you have there. We also have salts and electrolytes. Salts specifically are substances when you add to water, they dissociate, but they don't dissociate into H+ or OH-. They dissociate into metals and other metal ions like sodium or magnesium or potassium or calcium, things like that. So in order for a neutralization reaction to take place, you would need to add equal acids and bases together. And what you would do in that case is you would form, in this particular case, you'd form sodium chloride because those two would come together. And the H plus and the OH minus would come together, you'd get water form. And that's going to be a neutralization reaction. That's an official one. When it comes to electrolytes, we all know that we need them in some sense, probably some general feeling of that, but they help conduct electricity in your body in all sorts of different ways. So sodium and potassium and calcium are going to play a big role in lots of things that take place in your nerve cells and your muscle cells. And then the other ones are important for balancing those things out too. And we also have electrolytes that are important in our bones and in our teeth and lots of other good stuff. And Veronica, I know you got your blue stuff, so you know about that. All right, so before next time, make sure you complete chapter 2.3 stuff. We're getting into organic molecules next time, so definitely coming prepared is going to make a big difference. So on Blackboard, that's 2.3, chapter 2.3. It's like the last part of module 2. What do you have to do before you come to lab next time? What do we have to do before lab on Wednesday? The pre-lab, your turns, the flow chart of the procedure, and we did the your turns in the pre-lab quiz, If by some crazy thing you haven't completed discussion board post 1 or no 3, make sure you get that done as soon as possible. If you haven't done lab 0 yet, definitely get that done. That's urgent because that's going to set the stage for the entire semester. I think most of you have done it. I think there might be a few that haven't done it. Just make sure you've done that. If you haven't completed the whole orientation assignment for some strange reason, just get that done too. I've sent personal emails out to some of you, but I don't know if I've caught all of you yet. I don't know if some of you have caught the emails I sent to you. So please do that. Remember the bonus possibility of going over there to the learning lab. They're going to be really helpful. This lab takes a lot of preparation, so make sure you take some time to get your procedure written out, your flow chart. Also, serial dilutions and parallel dilutions, sometimes they're like not that easy to visualize. So take the time to work through the handout. Take the time to watch the videos that are in the handout. They're going to be very, very helpful. And that's all I got to say. Enjoy the beautiful weather.
Yes, I just want to take this time to show you my better preparation. Yes.
Okay.
Yes. This is how hopefully I would have come in last week. But I do have a question. I did take the time to fill out the lab one, just so I could have like all the information on it, but on here.
Let me stop the recording.